recording, I think. Okay, cool. All right, so as you guys requested, you said, okay, I want homework help. Specifically, I want help with problems that are proven difficult on the homework. So it makes it tough for me because your homework is obviously due on Mondays, and for me to release a video knowing full well exactly what's a problem, I'd have to wait until like Friday or something to know exactly where students are going on. But I can now assess a few things that people have tried and seem to be proven difficult. And then also I add in some questions that are on future exams that sort of hinge into those things. So that's what this is going to be about. And I might release a video later to do with labs. But you guys are very good at emailing me about labs, so I need to know if that's something you would like to continue, maybe having email be more reserved towards labs and these be reserved for more like homework part help. So I'll do a bit of a survey later. So first things first, what's entropy? Because that's what this whole unit is about. And entropy is essentially a system that wants to be more spontaneous. And when systems want to be more spontaneous, it's akin to saying it wants to be more like the universe and more at one with its surroundings and blah, 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 blah. And what we really care about is that means it has a negative Gibbs free energy, almost always. It usually is exothermic, sometimes can be endothermic. And all of that then depends on the temperature. So when I think of measurements of spontaneity, I look at Gibbs free energy, which is reliant upon the enthalpy of the reaction as well as the entropy of the reaction and the temperature directly. And as well, we know that Gibbs free energy also equals negative gas constant times temperature times the natural log of the equilibrium constant. So it also has to do with how much you have of something. And this is something that we have kind of alluded to in previous things where we'll say, oh, why is this side favored? And why is there that negative x and plus x in the shift that we see? And that has to do with how many moles of something is on the other side. And that is why that also relates to Gibbs free energy, and that something is going to want to go towards the more spontaneous side when we don't know the measurements. So that's what that was all about. It literally was measuring entropy. We just didn't have a name for it yet, and it wasn't a concept that you had learned yet. So that's what we're now going to go back in a way and teach more thoroughly. So when I look at this question, this is a common question. It says, if the change of entropy of the surroundings for a process happens at a specific temperature, right? And we have this constant pressure here. Oh, sorry, it's kept at constant pressure, so we don't have to worry about pressure changing because pressure does affect the equilibrium constant, right? So we're saying that's not an issue. And it's like, okay, I have negative 348, blah, 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 change in entropy. So what's the quantity of heat absorbed? Okay, well, I'm going to get out my pen here. What I know is I have two numbers. I have a temperature and I have a change in entropy. And I'm kind of going to remember here that there is an equation where the quantity of heat measured is literally delta S times T. Awesome. That's a very important equation. And once I know that, well, that makes this a lot more easy. So again, pressure is constant. That means we can assume the process is reversible, right? Because there's no tipping the scales here when we're doing that. As well, again, like I said, delta S equals the constant, the quantity of heat absorbed divided by T, aka quantity of heat absorbed is going to equal delta S times T. I know that when you change your entropy, this is your heat flow is then going to be positive for the absorbed and negative for released. Again, that alludes to something that you learned back with the enthalpy stuff. So that is something that has come up again. So be sure to note concepts that come up twice. It's very important. And also know that temperature is also always in Kelvin. All right, so I go through this. Delta S is the surroundings, which is equal to the negative delta S of the system for a reversible reaction. So some people mix this up. Negative delta S for a system of a reversible reaction. This is because the surroundings is equal to, the surroundings are going to be reversible. So it means that things that are lost to surroundings is reversible, so it can always go back. So then we always think of a negative delta S. So that is already noted up here as negative, but in the exam, sometimes they do not denote it as negative. So I've given it to you as negative here to keep things simple, but just note in the exam, you will have to know that. It says the change of entropy of the surroundings is this way, and that's because it's reversible. And you will know that because it's constant pressure. Okay, so again, this is the delta S of the surroundings. Then we know the opposite to that, the delta S of the system, is going to be the positive of that. So again, noting that change in entropy, if the delta S of the surroundings is negative, therefore it must mean that the loss or gain has to come from the system. So therefore, this would be the opposite sign. Multiply this by the temperature, and when we have quantity equals the system times the temperature here, you're going to get then the correct significance. Remember, this is the quantity of heat absorbed by the system. So I am looking at the system. This was from the surroundings. So that's why we've made that switch. All right, and then of course, always remember sig figs, especially in an exam where they make you input the number. Always do sig figs. I just realized I wrote this question up here behind my head. I wrote an equation over there. It's behind my head. I want to do this. All right. Predict how the entropy of the substance is affected in each process. Okay, cool. Very simple. All right. I have N2. It's a liquid. It's becoming a gas. Okay. I know that in a phase change, when I go from a liquid to a gas, if I have a bunch of things that are moving a lot slower and they start moving a lot quicker, it means the entropy of the process is increasing because things are becoming more disordered. Things are bouncing around here. So this means that the entropy is going to increase. All right, here. Again, I'm going from a gas to a solid. Now, based on our previous thing that we just said, if molecules start speeding up, bouncing around, and going crazy, it means that they're becoming more disordered. More disorder means more entropic. Here, the exact opposite is happening. So I would definitely assume then that the entropy is going to decrease. And the reason for that being is because it's slowing down, the carbon dioxide is having trouble bouncing around as crazily as it could before because it doesn't have the same energy. It's becoming more ordered, and more order means less entropy. All right, and then this one's a bit of a trickster because it's all in the gas phase, it's all at the same pressure here, so it's like, okay, well, what's different? Well, we've got 125 degrees to 200 degrees. Again, if I look up here, I went from 75 Kelvin to 100 Kelvin. I increased my temperature. Whenever you increase the temperature, especially with gases, you'll note the gases just speed up and become more bouncy and crazy. And that, again, would be indicative of an increase of entropy. So whenever you see gases and increase in temperatures, normally that is akin to a more entropic process. So just keep that in mind. All right, next, we're going to consider each reaction and predict whether the sign for delta S of the reaction is positive, negative, or around zero. So when I think of this in general, before I show any examples, something that I would already have in my brain is, what does delta S of a reaction positive, what would that look like? What would that be? And then it's like, okay, and what would negative be? And what would that look like? And what would around zero be? All right, so my first one. So I'm looking at this here. I know delta S measures things that are going to become more entropically favored, so something that's going to become more disordered. So in this one, if I look at these two things, I have two things becoming one thing. Already that to me akins to something becoming more ordered. And another thing here is I have bonds being formed. Again, more ordered. So I would think that delta S is not so entropically favored anymore. And in fact, I would think delta S would then be negative. It's not becoming more entropic, it's becoming less entropic. So this one right here, for me, I'm going to put this in a pen, is negative. Negative delta S. Cool. All right, next one. Ooh, this is a doozy. It looks a bit funny, but we can see the general idea here. I've got a 4 bonded, what's it called? A little butane-esque looking thing. And it bonds with this hexane here, and it opens up the ring. So we are ring opening. Okay, if I'm opening up a ring, that means I'm breaking a bunch of bonds. I'm breaking this bond, I'm breaking this bond's going to move up here, blah, 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 blah. You don't need to know all the fun, disgusting organic chemistry that's going on here, but what you do need to know is that bonds are breaking. And if bonds break, that is meaning that it's becoming more entropic. It's becoming a bit more crazy in here. Yes, I went from 2-3 things to one thing, but specifically, I broke a bunch of bonds along the way. And what I haven't shown, and what this reaction scheme, I guess, has not shown you, is that there's actually this whole ruthenium complex that is left on the side. You've got some hexane that was chopped off along here, so there's a lot of extra parts. So what this is specifically trying to show is that even though I've got more things over here and less things over here, because I broke more bonds than I formed, this therefore is going to have a positive delta S. Because essentially I broke this ring apart. All right, now kind of like going along with my theme, okay, if I did a positive and negative, this one's probably around zero, whatever. But the reason why this is around 0 and why I wanted to point this out is because you can note that the bond is moving here and it's now here, right? And I saw that this H went floop up into this oxygen. Again, we don't care about the organic chemistry, but what I do want to note is the bond that broke was then formed again, right? This double bond broke, but it formed a double bond here. So the amount of bonds breaking and forming was the same. One broke and one formed. And therefore, because we have one broke and one formed here, this is overall going to be about 0. So when you're noting these, just go through and be like, okay, well, how many bonds broke and how many bonds formed? If more bonds were broken, probably going to be a positive. If more bonds were formed, probably going to be a negative. And if the same amount was formed and broken, then it's probably about 0. We say around 0 because being exactly 0 for entropy is actually very difficult, but what we mean is like 0.01, 0.03, negative 0.03, etc. Around 0. All right, this one is one that you're going to see on your homework a few times, so I definitely want to go through 2 examples of it just to get it out of the way. So it's going to say, you use data from this table of thermodynamic properties. I'm not showing the table of thermodynamic properties because it took too much space up on my slide, but you will be given a table of thermodynamic properties, so just be sure if you get this is wrong, before emailing me, double check your math, because it's not a problem for me to go through your math and show you where it is, but it sucks that you're like panicking for a minute thinking you don't know something because this is a bit more straightforward, only to find out that it actually was a math error. All right, so I got 2 problems here. I already want to note in these problems with my pen that we've got a bunch of coefficients, and these are how these problems usually go. They just swarm them with coefficients. So you need to be sure that you stay on top of your coefficients when you are doing this. Sorry, my one is a mess. It's always a mess though. It looks like 7 sometimes it doesn't. So, ooh, this popped up when I didn't want to. So what I wanted to know is that the standard of a reaction is always going to be products, the sum of the products, minus the sum of the reactants. So we know that this is standard molar entropy, but we know that these are going to be your coefficients. So you're always going to take these down. So note, here are my products here, and I have 4 times NO2, right? The entropy of NO2, which this value I'm going to get from my table here. So this value comes from my table, this value comes from my table, but these are coming directly from my equation. I notice this is 4 times the entropy of this ammonia, and then 7 times oxygen. So I plug these numbers in. Again, I got these values from the table of thermodynamic properties. I plug them in. Again, products subtract reactants. And I should get negative 114.4. Note, joules per mole per Kelvin. This is because the change of delta S in a reaction is always going to have your moles. Sometimes, in your homework included, they are going to give you moles, in which case you would have to then multiply this by the number of moles. So we're going to put N, and then you're going to put moles. Right? And then this is going to give you S, reaction. Okay, so this is number of moles. All right, moving on. Same idea, I plugged this in, I got my coefficients that I got from above. 1 was in front of my oxygen, so I plugged that in. To subtract, the reactants, my hydrogen peroxide. I plug in these numbers that again I got from my table, and I got 126. Something I strongly recommend is when doing these problems is double checking your math, but also being sure that when you do this process that you are counting everything correctly. Double check the table, because sometimes you swear that hydrogen peroxide is 109.6 joules per mole per Kelvin, and then it's not. You'll go back and you're like, that was H2O. So just be sure the values that you're getting from the table match up. All right. And the last thing I wanted to go through was one of these true or false questions. This is a very, what's it called? The exam questions, the very exam question. Which of the following statements regarding spontaneous processes is not true? All right. Why I wanted to go through this one is one that a lot of people missed. And I think it's because of when we think, and it's something that I said very much at the start of this, when we think of spontaneous reactions, we think they're going to be something that is a hard and fast rule, and that's not always the case. So I looked through the spontaneous reaction processes are exothermic. Spontaneous processes proceed without outside intervention once initiated. Okay, I look at this and I'm like, there's such things as catalysts. So I already read B and that just sounds ridiculous. Spontaneous reactions are not always rapid. That is actually very true. So it's like this one. Always, processes proceed without outside intervention once initiated. There's such a thing as catalysts, so they can proceed with outside intervention. Here, spontaneous reactions are not always rapid. This one is not so straightforward, but this one, it has to do with difference in the activation energies, differences in the temperature. So the reason why spontaneous reactions are not always rapid is due to the nature of the reaction, which I think are going to get into lecture either this week or next week. But you will learn that this one actually is true. So I'm going to cross that off because, again, remember, we're looking for not true. Not. All right. The motional freedom of particles tends to increase during spontaneous change. Well, as we just said, when we increase temperature, which if I go back here, when I'm increasing the temperature, I am then going to make my particles move more, which is what we call motional freedom. And when it's moving more, then it's going to be more spontaneous. So when I do that, I'm like, okay, oops. So it's like this one's true, and this one's true. All right, and then particles tend to become more spread out during spontaneous change. This sounds a bit funny, but it is true. They do tend to become more spread out during a spontaneous change, and that's because if you think about going from a solid to a liquid to a gas, they are going to be moving further apart. Liquids lay on top of each other. Solids are compact next to each other. Gases are in space. And then the faster they move, the more in space they are and the less they interact with each other. So this is true. It just sounds very odd. So the only thing that's not true is that spontaneous processes are exothermic. And the reason that this is not true is because spontaneous reactions can also be endothermic. It just depends on the circumstances, because remember, delta G equals delta S minus T delta S. So it just depends on the magnitude of the enthalpy in relation to the magnitude of the entropy of the system. And if they cancel each other out, you could actually get a negative Gibbs. Depending, like if you have a very, very positive delta S, you could have an endothermic process. It just doesn't affect the entropy as much. It's the magnitude of the enthalpy and the magnitude of the entropy that matter. All right, I think that's all. So that is all I have for you. Thank you so much, and I will see you, and I will see you guys next week. All right.